Okay, let's dive into this. We are looking at a phenomenon that is fundamentally altering the raw power of nature right here on our planet. Today, we're going to break down the exact mechanics behind the supercharged future of tropical cyclones. If you want to understand how our changing environment is literally rewriting the rules for extreme weather, you're absolutely in the right place. So, what actually fueled the catastrophic destruction of Typhoon Haiyan? Before we can even begin to model the future, we have to look at the visceral, on-the-ground reality of what happens when a storm is pushed to its absolute limits. We're talking about a real-world disaster that shattered records and, tragically, shattered communities too. To understand the mechanics of tomorrow's storms, we really need to uncover the invisible engine that drove one of history's most devastating events. Section 1. Remembering Typhoon Haiyan. Back in 2013, Typhoon Haiyan struck, and man, it established an incredible, terrifying baseline of destruction. This was a Category 5 storm, packing sustained winds of nearly 200 miles per hour. Just to put that into perspective, that's like an Indy car racing through a neighborhood. When we look at the data from this event, we aren't just looking at a bad storm, we're looking at a complete atmospheric anomaly. It represented the absolute peak of what a cyclone could achieve at that time. But actually, the most important part of Haiyan's story isn't just the wind or the rain, it's how it got so incredibly powerful in the first place. Haiyan was driven by remarkably warm ocean waters. And this is the absolutely critical link here. Tropical cyclones are essentially just giant heat engines. As ocean temperatures rise, more water evaporates, transferring massive amounts of what scientists call latent heat right up into the atmosphere. That thermal energy, that's the direct fuel that spins up a storm's vortex. The ocean's heat was the key driving force behind this specific disaster, and it essentially set the stage for exactly what we are seeing globally today. Let's move to and see how this builds in Section 2, the ocean energy engine. All right, here is the core mechanic at play. I want you to think of the warming ocean as a massive, overflowing fuel tank. Today's significantly higher global temperatures are actively supercharging our atmosphere. Because of human-caused global warming, modern cyclones now have access to much, much more of this thermal energy. When you've got more heat trapped in the ocean, you have massive potential energy just waiting to be transferred up into the sky. It feeds directly into the developing cyclone, honestly, exactly like an ocean-powered combustion engine. And this brilliantly illustrates a widely misunderstood point. The total number of storms forming per year, it isn't necessarily rising. The frequency is actually staying relatively flat. But the available thermal energy, wow, that is skyrocketing. The stark contrast here is just fascinating. While we aren't seeing more storms forming overall, the ones that do form are pulling from a dramatically deeper well of high-octane fuel, meaning their underlying raw power is significantly higher. So, what does this all mean when a storm taps into all that excess thermal energy? Well, we get a direct cause and effect, rapid intensification. This is a genuinely terrifying metric where a storm's wind speeds just dramatically spike in a very short period of time. We're talking jumping whole categories in under 24 hours. Because of the vast thermal energy available in today's oceans, modern cyclones can rapidly intensify into ultra-powerful threats before coastal communities even have a chance to properly prepare. The extra fuel doesn't just make them stronger, it makes them stronger way, way faster. Section 3. The supercharged future. So the crucial point is understanding exactly how this extra energy manifests physically in the real world. Based on the data, there are 3 terrifying expectations for future storms. First, faster wind speeds, tearing through infrastructure with way greater force. Second, roughly 20% more rainfall just dropping from the sky. And third, much deadlier storm surges pushing further inland than ever before. This is the direct, unavoidable result of an atmosphere supercharged by higher global temperatures. Now, what's really interesting about this slide is that seemingly small number right there, 20%. Because physics dictates that warmer air can hold exponentially more moisture, that 20% increase, when applied to the sheer massive volume of water a cyclone already dumps, translates to catastrophic, widespread flooding. It means drainage systems failing, rivers instantly overflowing, and communities literally drowning under the weight of an atmosphere that can simply hold and release so much more water, all because of that excess heat. Which brings us to a really sobering comparison. The total destruction of Typhoon Haiyan was an absolute worst-case scenario back in 2013. But because of this massive, continuous increase in thermal energy, the ultra-powerful systems of tomorrow are expected to easily match or outright surpass it. Haiyan is no longer an anomaly, folks. It's becoming the blueprint. It's the new baseline for the extreme weather systems of our future. So, it leaves us asking, Are we prepared for a future where the destruction of a Category 5 storm like Haiyan is just the beginning? We've seen exactly how human-caused global warming provides the thermal energy that supercharges these cyclones, driving faster winds, heavier rains, and much deadlier surges. The mechanics are crystal clear, and the fuel tank is absolutely full. Thank you so much for joining me for this explainer. Keep learning, keep analyzing, and I'll see you next time.